Good day, sir. Today I will be presenting the classical methods of analysis and the techniques of metallurgical analysis. These methods are among the oldest, but still are very important techniques in determining quantity of metals in ores and samples. Classical methods of analysis are techniques used before modern instrumental methods were developed. They rely on wet chemistry, gravimetry, and titanometry to determine the concentration of a certain metal. In this presentation, we will cover copper acide, zinc acide, lead, and iron acide. First, I will explain the classical method of analyzing copper in ores and samples, also known as the copper acide. This process determines how much copper is present in a given sample. The principle of copper assay is based on isolating copper from other elements then measuring it. A common method is isometric titration, where ions react with potassium iodide, producing an iodine that can be titrated with sodium thiosulfide. The reaction equation: 2 moles of copper ions react with 4 moles of iodide ions to produce 2 moles of copper iodide and one more mole of iodide. Here we have the flow chart of the steps in copper acid. First is the sample preparation. The procedure of copper acid generally follows the steps. The first, preparing the sample, then dissolving it in an acid, separating copper from impurities, determining copper either by precipitation or by titration, and finally the calculation the copper content. So in detailed procedure, the ore sample is dissolved in a nitric acid. Potassium iodide is added. We reduce copper to corpus iodide and release iodine. This iodine is then titrated with a standard sodium thiosulfate solution. A starch indicator is used where the blue color disappears at the endpoint, signaling the reaction is complete. So in calculation, we have the formula: the percentage of copper times V, which is the volume of thiosulfate used, times N, the normality of thiosulfate, and times 31.79 times 100 over weight, which is the weight of the sample. After the titration, the copper content is calculated using this formula. The percentage of the copper is determined from the amount of thiosulfate consumed, its concentration, and its weight of the sample analyzed. Key points. Isometric methods, it is precise and it is suitable for high copper bonds. In summary, copper assigned through isometric titration is a reliable classical method. Involves dissolving the sample, reacting copper with potassium iodide, titrating the released iodine with thiosulfate, and calculating the copper percentage. This method is still widely respected for its accuracy. Next is the lead assaying, which is classical method of determining lead content in ores, particularly in galena, the most common lead mineral. The principle of lead assay is gravimetric method or determination. Lead ions are precipitated as a compound with known composition, such as lead sulfate or lead chromate, which is then filtered, dried, weighed, and used to calculate the amount of lead in ore. Reaction example: lead lead ions plus sulfate ions yield lead sulfate, which precipitates as a solid. Here is the steps in lead assigned shown in the flow chart. The general steps are the preparation of the ore sample or the lead, solving it in a nitrate acid, precipitating the lead, filtering and drying, and precipitation, and then weighing it to calculate the percentage of lead present. The general steps in lead acid including the preparation of the ore sample, the dissolution of nitric acid, and the precipitating the lead, filtering and drying the precipitate, and then weighing it, calculate the percentage lead present. So here is the detailed procedure. The ore sample is first dissolved in a nitric acid, form a lead nitrate. Then sulfuric acid is added, precipitating lead as a lead sulfate, a white crystalline solid form. The precipitate is then filtered and washed, dried, and finally weighed. So we have here the formula. The percentage, the percentage of the lead is calculated using this formula. Since the precipitate is PbSO4, the atomic weight of a lead and compound are used to determine the exact lead content. In summary, lead aside is that through gravimetric precipitation, where lead is isolated as lead sulfate, the precipitate is carefully weighed and the lead content is calculated. This classical method is valued for its precision and reliability in analyzing lead ore. Now let us move on to zinc assaying, which is the classical method of determining zinc content in ores, most commonly from sphalerite or zinc blending. The principle of zinc assay is based on the compleximetric titration with EDTA, or the EDTA, a chelating agent that forms stable complex with zinc ions. The amount of EDTA requires to completely bind zinc corresponds to the zinc content of the sample. Steps in zinc assay. First is the sample preparation, dissolution in acid, buffer solution adjustments, the pH 10, titration with EDTA using an indicator, and lastly, the calculation of zinc content. In procedure, the ore is dissolved in acid to produce zinc ions in solution. An ammonium buffer is added to keep the pH around 10, which ensures accurate titration. An indicator such as aerochrome black tea is used, changing from red to blue at the endpoint. The solution is then titrated with standard ENDA until the color change signals completion. The formula for the calculation, the percentage of zinc is equals to the V, a volume of ENDA used, and the normality of ENDA times 65.38, which is the atomic weight of the zinc, times 100, over the weight, which is the weight sample of the zinc. Complexometric titration and the method are highly accurate for zinc ores. In summary, zinc assaying is carried out using a complexometric titration with EDTA. This method is precise, reliable, and widely applied in analyzing zinc ores such as sphalerite. Now, lastly, is the iron assay. The principle of iron assay is based on the redox titration. The ferrous ions are oxidized to ferric ions by potassium dischromate in acidic medium. The amount of dischromate used is directly proportional to the iron content of the sample. We have the reaction. The 6 moles of iron ions react 1 mole of The chromate ions in the presence of 14 moles of hydrogen ions to produce 6 moles of iron ions, 2 moles of chromium ions, and 7 moles of water. The steps in iron acid includes the preparation on dissolving of the sample in a hydrochloric acid, reducing all ferric ions to produce forms, nitrating and with standard potassium discriminate, finally calculating the iron content. The detailed procedures. So in the practice, the ore is dissolved with hydrochloric acid. A reducing agent such as stannous chloride is added to ensure all iron is in the ferrous state. Exceeds reducing agent is removed by mercuric chloride and the sample or the solution is then titrated with potassium dischromate using an indicator like a diphenylamine, which produce a distinct color change at the endpoint. Now we have the formula for the calculation with the percentage of iron, and V is the volume, N is the normality, and then W is the weight. And we have 55.85 as the atomic weight of our iron. In summary, iron assigned is performed using redox titrations and potassium discrete. This classical method is accurate and widely applied in determining the iron content of ore samples. And there we have it. The four classical methods, the copper acide is hydrometric titration, the lead acide, the gravimetric method, zinc acide, the complexometric titration, and the iron acide, the redox titration. Next,